Now, Euler's theorem tells us if a connected graph contains an Euler path or circuit. However, there is no theorem or method that does the same for a Hamilton path or circuit. But if a graph is a complete graph, and I'm just going to write it down up here, a complete graph. And a complete graph is a graph with more than two vertices that has edges that connect every vertex to every other vertex. So if a graph is a complete graph, then we can determine how many Hamilton circuits are possible in the graph. So for this example, it says determine the number of possible Hamilton circuits on the complete graph. And we can tell that this graph is a complete graph. If you go to vertex L right here, you can see that it has an edge connecting to vertex M. It has an edge that's connected to vertex P, an edge that's connected to vertex N, and an edge that's connected to vertex O. And if we go around to each vertex, we'll see that that's the same. M has an edge to L, M has an edge to O, M has an edge to P, and of course has an edge to vertex N. And each one is connected, so this is a complete graph. And since it's a complete graph, we can determine how many possible Hamilton circuits there are. And we do that by counting up the number of vertices. So we have 1, 2, 3, 4, 5 vertices. So we say that the number of vertices is 5. So if the number of vertices is 5, then the way we determine how many circuits there are, how many Hamilton circuits there are, we can go ahead and we can say n minus 1. And then we have this exclamation point factorial. And a factorial, I'll write it right here, is where you take a value, a number, and you multiply it counting down to 1. So for this example, if we have 5 vertices, then we have 5 minus 1 factorial, and 5 minus 1, that's 4 factorial. It's this exclamation point. So what is 4 factorial? Well, this is a shorthand for 4 times 3 times 2 times 1. 4 times 3, that's 12, times 2, that's 24, times 1, so that's equal to 24. So there are 24 possible Hamilton circuits for this complete graph here. Now, as the number of vertices goes up, the possible Hamilton circuits tends to skyrocket. So if you could imagine if we had 6 vertices, then we would have 6 minus 1 factorial. That's equal to 5 factorial. And what's 5 factorial? Well, that's 5 times 4 times 3 times 2 times 1. Or we can think of it as 5 times 4 factorial. But this winds up being 120. If there were 7 vertices, then there would be 7 minus 1 possible circuits. So that's 6 factorial. So what's 6 factorial? Well, that would be 6 times 5 times 4 times 3 times 2 times 1. That would be 720 possible circuits. So you can see it starts to inflate very fast. But for this particular problem, determine the number of possible Hamilton circuits on the complete graph. Well, if there are 5 vertices, then we use 5 minus 1 factorial. 5 minus 1 is 4. That's 4 factorial. And 4 factorial is equal to 24.